Good evening, viewers. Welcome to Quest. The program has been jointly organized by the National Council of Science Museums and Calcutta Doordarshan. Like in previous programs, we have today also two teams. On my left, we have the Einstein team, and on my right, we have the Bose team, ASN Bose team. They are represented by the students of class 11 and 12 of different schools of Calcutta. Now, you might remember that in the last Quest program, we had put to the viewers one question. The question was like this. You see, the water is boiling. In this flask, there is water, and it is heated, and the water is boiling. Now, the steam has displaced all the air. I put off the switch, and then I close the mouth of this flask. I close the mouth of this flask, and you see the boiling gradually stops. Now I shall cool this flask by pouring cold water on it. You find that the boiling has stopped. Now I pour cold water. Please put cold water. Pour it, and you see, stop it. You see, it starts boiling again. My question to the viewers was, why does it boil by cooling? We know that when you heat the water boils. Pour it again. Pour it again. Okay, fine. We have received many correct answers from students all over India, and I shall try to answer it. Now, when I cool the flask, what happens? There is steam inside, and the steam condenses. When the steam condenses, there is partial vacuum inside. And we all know that water boils at a lesser temperature when the pressure over the water is less. Now, the reverse takes place. You all might know, you might all have seen in your kitchen while cooking in a pressure stove. When you close the lid and heat this pressure cooker, then the pressure increases inside and it boils at a higher temperature, so the things boil or cook very quickly. So this is the answer for the last question that I had placed before the viewers. Now I shall start today's Quest program with the question to the Einstein team. Now I have here two jars. Einstein team, this is for you. In this jar I have some water. Can you see it? Now I have a bottle of soda water. Now in this water I place a naphthalene ball. This is naphthalene ball. And I open the soda water. Just a minute. And then I place, now you see, it went down and this has again come up on the surface. Now you watch what happens. Now in this, of course, in water, the naphthalene ball is there at the bottom. But in soda water, the naphthalene ball has come up. Now it is dancing. Let us see what happens. Takes a little time. Now my question to the Einstein team will be, we will observe this experiment, that after some time this ball, yes, it is coming down and it is coming up, it is dancing. My question to the Einstein team is, why the naphthalene balls behave in a different way in water and in soda water? Here in water it is there at the bottom, but here in the soda water the naphthalene ball goes up and down and it dances. 30 seconds for the answer. You have to give the full physics behind the experiment. So 25 seconds gone.
Because of the carbon
Are you
dioxide,
ready? Okay, please.
because of the carbon dioxide vapors which come up, carbon dioxide gas,
Yes.
which sticks to the naphthalene balls,
Yes.
it makes them more buoyant.
Yes.
So it goes up and floats in the air.
Okay, then.
So when it comes to the surface, some of the carbon dioxide bubbles that stick to it, they get detached.
Ah.
They come in contact with the air.
Yes.
Then they become less buoyant, they come down. Again, the more carbon dioxide.
Wonderful. Give a clap to him. Wonderful answer. Yes. But in water, because the weight of the naphthalene ball is more than
than
the
water.
upward thrust, it goes down. Now here they have explained absolutely correctly that when it is placed in soda water, the carbon dioxide gas accumulates over the surface of the naphthalene ball. As it gradually accumulates, the volume of the naphthalene ball goes on increasing and the upthrust goes on increasing. So when it is more than the weight of the naphthalene ball, it moves up. Then the carbon dioxide escapes in here. Again the naphthalene ball becomes heavier and it becomes more than the upthrust, it goes down. So it is like this. So next question by Dr. Ghosh.
This question is for the S and Bose team. We have water in these two perspex beakers and they are more or less now balanced, as you can see. Okay? Perhaps I should take out a bit from here. Is that all right? Right, now it is balanced. Now, I have a weight here. Its volume is approximately 7 cc. I'm going to introduce this into the water here. I'm going to immerse it. Now, you will have to predict what is going to happen. Will there be any change? If so, in which direction and by how much? 30 seconds. Time is nearly up. Have you got the answer?
Yes.
Yes, what is the answer?
The beaker in which you're introducing that solid thing,
Yeah.
that's going to go down.
By how much?
It's going to go down by
Quick.
the weight minus the tension that you're applying upwards.
No, you are only partly right. Would you like to answer the rest of the question? By how much?
Weight of 7 cc of water.
What is that?
7 grams.
So it's going to go down by 7 grams.
Yes.
Okay. So, okay, you have to explain why now. Why does that happen?
When you introduce that into the water, there's upward thrust acting on it due to Archimedes' principle. And due to action and reaction from Newton's third law, that same solid substance is going to exert an equal force in the downward direction, which carries undiminished through the water and exerts itself directly, normally, on the bottom of the container.
Good, very good. So, But since you got only half of the answer right, I'll give 5 marks to each team. Do you know why it's depressed by 7 grams?
Because the volume it is displacing is 7 cc's, and by Archimedes principle, it will exert an equal weight, the weight of the displaced mass.
Okay, but why is it 7 grams?
Is the density of water.
Okay, fine. Okay, so 5 marks to each team. Now, let me verify and see whether you were right. I'm going to introduce it into the water here. Yes, you are right, it's gone that side. But how do I know it is 7 grams? Well, I have here with me a 5 gram weight, which I'll put here. And I also have a 2 gram weight ready for you. I'll put it there. So now you see the balance is restored. Okay? And when I take it out, you see it goes the other way. So that's absolutely correct. Now let me explain the answer for the benefit of the viewers. See, when we introduce this object into the liquid, it displaces an equal volume of water. And by Archimedes' principle, therefore, there is an equal upward thrust on this object. Now since its volume is 7 cc, it displaces 7 cc of water, so there is an upward thrust of 7 grams. But because of Newton's third law of motion, this object exerts a downward force of 7 grams on that pan, and so the pan goes down by 7 grams. Okay, that's fine. Next question by Mr. Bagchi.
Now this will be a common question to both the team, Einstein team and Bose team. You find that a book is hanging from a bridge. Now what both the team has to do, you will be given 30 seconds time. You have to make this book swing to and fro without touching the book by hand or by your body. You have to make it swing with a greater amplitude. The amplitude should be this much. You understand? You have to make it swing without touching the book, and you have to explain the principle, how you can make it move with a greater amplitude. Fine? 30 seconds. Yes, you can, but you can't touch. You have done it? Okay, so they have done it. Now you have to explain. You can try, you can go on trying, but you have to explain what is happening. How can you make it swing with a greater amplitude?
Greater amplitude is what?
This
normal.
Yes, because you are making it move with a greater amplitude. So what you have to do to make it move with a greater amplitude?
Air is pressure.
Air is pressure.
We are exerting pressure on it.
Yes.
So naturally it's going to move.
But if you exert pressure in any way, it will go on giving oscillation and it will go on increasing?
No.
So that you have to explain quickly. It will not move with a greater amplitude if you blow haphazard way.
The particular way of blowing the air is in such a manner so that there is a resonance out here.
Wonderful.
And the resonance is going to go on making it move.
Correct answer. Full mark to the Bose team, and they get 10 marks. So the Einstein team has got 15 marks and Bose team is also 15 marks. Now I shall explain it for the benefit of the viewers. Now you see what they said is you have to blow it in resonance. That means your blowing should have a frequency which is in step with the frequency of the book, like this, like that. Now you might remember that when a battalion of soldiers is moving over a bridge, they are asked to break the steps. Why? Because every object has a natural frequency of vibration. Now if the natural frequency of vibration of the bridge and the frequency of the step becomes same, or the frequency of the step is a multiple of the natural frequency of vibration of the bridge, then a larger vibration may be set up in the bridge and the bridge may collapse. That's the reason why the soldiers are asked to break the steps. So full mark, 10 mark to the Bose team for this question. Dr. Ghosh.
Now this question is again for the SN Bose team. You see, I have here a ring magnet, okay? A ring magnet. And also I have an ordinary bar magnet. This end is the North Pole and that end is the South Pole. Now, if I bring this ring magnet near this bar magnet, there is an attraction. That means that this face is the south face and that face is the north face, and there is an attraction between the North Pole and the South Pole. I'll show it once again. Okay? However, if I slip this ring over this magnet, see what happens. It's rejected. I'll do it once more. It's rejected. If I turn this ring magnet so that this is the North Pole and this is also the North Pole, if I bring the two together and slip it over, you see what happens? It's inside. It's also the same from the other way. Okay? Now you have to explain why this happens. 30 seconds. Gone. 10 more seconds.
Yes.
Time is up. Yeah.
Initially, when you bring the magnet, the North Pole of the bar magnet towards the ring magnet, to the South Pole of the ring magnet, just because of attraction, North Pole, South Pole attraction, it gets attracted.
Yeah, that's fine.
Then when we introduce the bar magnet inside,
Yeah.
there is, due to Lenz's law, what we get there is
Lenz's law.
I'm sorry. I mean, there's an induction of North Pole North polarity in the magnet inside that ring, which causes North Pole repulsion ultimately.
No, I'm afraid the
South
answer
pole of one magnet
which south?
attracts the which one is?
That's the south and that's north. But if I put it inside, it's rejected. Okay. Can you answer? Yeah.
When the North Pole is just introduced into the magnet, while the South face is facing it, then when it is just passed through the ring, the North Pole is closer to the North Pole of that magnet,
Yeah.
near the other face. So the North Pole is closer to the North Pole, there is repulsion in that
But
case.
the repulsion should be this way. Why is it coming towards the North Pole? You see, it's coming towards the North Pole.
Because there's a North Pole, there's a South Pole.
Yeah, but if that is the North Pole, and that's the North Pole, it should repel, it should go this way. Why is it going the other way? No, I'm afraid you don't have the answer, so no marks to any team. And I'll explain. It is a bit difficult. I'll explain this with the help of some diagrams. Now let's go to this board first. See, you have a magnet and there are lines of force, okay, from the north to the south and then inside in the other direction. I have drawn the cross section of the ring magnet here. That's the South Pole, that's the North Pole, so the lines of force go from the north to the south. Now we know that in this case there is an attraction. Now you see here that the lines of force are in the same direction. So whenever the lines of force are in the same direction and there is an attraction, so if you hold on to the magnet, this will be drawn towards the magnet. Now let's go to the other board and see what happens when we slip the ring here. Again, this is the south, that's the north. Draw the lines of force again from the north to the south. And again you see that the lines of force are in the same direction. And therefore, there is again an attraction. So this is pushed this way. But when you reverse the polarity as here, then of course the lines of force go in the opposite direction. There is a repulsion between this and that, it's pushed this way. When it overshoots the middle, again there is a repulsion because of the same reason from this, and it stays at the middle. So that's the answer. Okay, next question by Mr. Bagchi.
Now, I find that after the fourth question, the marks equal to both the team, 15 and 15. So this is the fifth question to the Einstein team. Please put this inside the water. Now inside this large syringe, you find here a large syringe, and in the syringe I have concentrated salt solution which is colored red. And when I introduce it, you see the level of the concentrated solution is more than the level of water here. Do you find it? Now, I shall open the plug and you find what happens. Please open the plug. See, the colored liquid is gushing out, and you observe what happens after a little time. Now the rate of flow is decreasing, and then the water starts getting in, and then again the colored liquid goes in, then again water enters. So there is a oscillating liquid that is flowing here. Now my question to the Einstein team is, why this oscillation of liquid here in this case? 30 seconds time. Seconds. 20 seconds over. Wonderful oscillation going on still now. Are you ready? Plus, start.
Initially, the level was more, and the intensity was also more. So the water started downwards.
Means this liquid?
Colored water.
Okay.
The solution started downwards.
Wonderful.
And after some times, a stage comes when the weight, the pressure at the mouth of the syringe,
yes,
due to the colored liquid inside,
yes,
and the plain water outside,
yes,
is equal.
Yes.
And due to inertia, it overshoots that mark.
Wonderful. Yes. Then?
And then the pressure due to the colored liquid becomes less.
Yes.
And so the plain liquid gushes inside.
Wonderful. Wonderful. That's a marvelous answer. That's a marvelous answer. Yes, that is what is happening. So full 10 marks to the Einstein team. Now I shall explain for the benefit of the viewers. Yes, as he said, at first it was at a higher level, so this concentrated liquid, because its level is higher and also concentration is more, the density is more, so it goes down. But as it goes down, because the inertia of the flowing liquid, it overshoots the equilibrium point, and so the liquid goes down a little below the water level. So at that point, the pressure of the liquid at the mouth of the syringe becomes more, so the water gushes in. Then again, by the inertia of the flow inside, it moves, the level here moves up, and like that the oscillation continues. Now you might have seen such oscillation in the case of a pendulum, like this. It goes on oscillating till it is damped out. You have also seen the oscillation of a swing in a children's park. So this is an oscillating fluid. Next question by Dr. Ghosh. Fine.
That's a common question for both the teams again. Now, we have given certain things to both the teams. For example, there is this piece of paper which we have given to each team. A piece of paper, a rupee coin, a pair of scissors, and some gems clips. Each team has these things. Now you've got to make use of all or some of these and devise an experiment to demonstrate Galileo's law of falling bodies, which states that bodies of all kinds and weights fall equally fast provided they fall freely in vacuum. You get 1.5 minutes to devise this experiment.
You have to show the experiment.
Yes, you have to do and show it. If you want to do it, you take it up. need not use everything. Right, you've got it. The Einstein team has got it. Beautiful. Now give it to me. Well, you have cut the piece so small that I'll use a slightly bigger piece, but you have actually got the right thing. See, the trick is the following. You cut out a piece of paper which is slightly smaller or smaller than the coin, right? Now, of course, and then you place, if you drop these two separately, they will obviously fall at different rates. As you can see, 1, 2, 3. The paper takes more time to fall. Why? Now you have to answer this part before I give you the full marks.
When those two things are given let fall separately, due to the air resistance, the force on each of them is equal. But since the mass of the paper is less, since therefore the acceleration is more for that. So in that case, I mean the retardation is more. So it falls less separately. But when the one is placed on top of the other, the air resistance is cut off for the paper. So the only thing that comes into account is the gravity.
I think, yeah, I should give you full marks. That's correct. So what they say is this. You see, when they drop separately, there's a lot of air pressure acting on this piece of paper. So if you want to make it fall as fast as this coin, you have to cut out the air pressure below it. The easiest thing to do is to place the coin below the paper and then drop it. See? They drop together. I'll do it once again. So you place the paper on top of the coin and you drop the two together. You see? You place the paper on top of the coin and drop them together. And they fall together. Because as I said, the coin is cutting out the air resistance from below this. Fine. And if you drop them separately, you see again, the air resistance makes this fall slower. So that's the answer. Perfectly correct. So what is the score? Which team wins now? What is the score?
It was 15-15 before.
15-15, but you've got full marks for this team. So you have actually, so 35 and 15. So congratulations, the Einstein team, you have won. Now the last question, as usual, is for the viewers. Now I am not a smoker, but I have specially brought a packet of cigarettes for you, smokers. Now, I have seen smokers, as well as people who sell cigarettes, do a very funny thing. They take a pack of cigarettes and start tapping it like this. And lo and behold, 1 or 2 cigarettes start popping up. And they pick up the cigarette and start smoking. Now, it is very funny, isn't it? I'm tapping it downwards, but the cigarettes are popping up. Now, we do this quite instinctively. Even uneducated people do it quite instinctively. You've got to think about it and write to us, telling us what the physical principle is behind this. What is the physical principle behind this very simple and ordinary thing we do almost in our daily lives? Okay? However, remember that smoking is injurious to health, so please don't smoke too much, but we'll be glad to receive your answers. So good night, gentlemen. Thank you very much, boys and girls. Thank you.